when we think about the changes that occur when a material changes phase between solid, liquid, and gas, and what determines what state a material is going to be in, we have to think about the temperature at which it's at, the average kinetic energy of the particles that are involved, but also the pressure that it is exposed to. We know that gases are a compressible state, whereas liquids and solids are not. But anything that's going to cause the particles to be able to come closer to one another, such to the point that the intermolecular forces are going to actually be able to take over, these conditions are going to facilitate a phase change. And the strength of the intermolecular forces also comes into play with what exact temperatures are going to be needed for a solid to melt into its liquid form, or a liquid to vaporize into its gaseous form. And so all of these changes, whether we are breaking intermolecular forces or intermolecular forces are taking over, they all involve an energy change of some sort. Attractions forming cause a release of energy, whereas the breaking of attractive forces involves inputting energy. It's what we refer to as an endothermic process. And so a quick review of our different types of phase changes. We have, anytime you go from a solid to a liquid, we refer to that as melting. The reverse process from a liquid to a solid is referred to as freezing. Now, we are accustomed to thinking of water as kind of our standard bearer when we talk about any of these properties. So to us, the process of melting or freezing probably stirs up feelings of coldness. But it's important to remember that any solid to liquid or liquid to solid phase transition for any material, even metals that have melting points in the thousands of degrees Celsius, that technically can be called freezing when you go from molten metal to its solid form. So we want to kind of temper our association with those phase changes and a given temperature or a feeling. And we talk about going from a liquid state to the gaseous state. That process is known as vaporization. And there are two types of vaporization. One is boiling. That's probably one of the more familiar one. The thing with boiling is that it will only occur at one temperature, but the temperature it occurs at is determined by the atmospheric pressure. Whatever the atmospheric pressure is, once the liquid has been heated to a point where the molecules that are evaporating, that are vaporizing at the surface, are of such a quantity that the pressure they're exerting is equal to the atmospheric pressure, then boiling can occur, and it can occur anywhere within the liquid. So that's why when you're heating water for spaghetti, usually you see the bubbles forming at the bottom, which is closest to the heat source. Evaporation is another vaporization process. This can occur at any temperature, even temperatures where you would expect the liquid to be in its solid state, like on a cold day, wet pavement will evaporate to dryness when you might ordinarily think it would be more likely to freeze. The thing with evaporation is it only occurs at the surface, but it can do it at any temperature. So that's kind of the give and take with boiling and evaporation. The reverse of that process, going from a gas to a liquid, is referred to as condensation. If we consider the transition from a solid to a gas, not normally what we think of, we usually think the progression is solid, liquid, gas, but for some materials at room pressure, they will completely bypass the liquid state and transition between solids and gases. Dry ice, carbon dioxide is one example of a material that does this. When something goes from the solid state directly to the gas state, that is known as sublimation. And when it goes from the gaseous state back to the solid state directly, that is known as deposition. One common diagram that we see when we're talking about phase changes is known as a heating curve diagram. Sometimes it might be called a heating or cooling curve diagram, and we'll talk about the difference between those two. But when we look at what the graph is showing us, obviously it's showing us temperature on the y-axis, but along the x-axis we see that as we move from left to right, heat is being absorbed. So as heat is added to a material, we see that when we are in a singular state, solid, liquid, or gas, which we can see represented here, okay, in the sloped regions, okay, the temperature is increasing, the y value is changing. But at places where we see indicated a phase change, notice that the temperature doesn't change at all. And so to understand why this is happening, we need to think about what are the energy changes that are happening as we are adding more heat. And so here we see a diagram that shows that heating curve, but at the same time it shows us what are the particles doing at a particulate level. And so for each of those sloped areas, okay, where you have a non-zero slope, these are the areas associated with a single state: solid for the lowest temperature slope, liquid for the mid-range slope, and gas for the highest range slope. And so in those sloped areas, the temperature is changing. That means the average kinetic energy is changing. And so within those areas, you have only one phase that is present: solid, liquid, or gas. To calculate the amount of energy that's needed to make a change, to change the temperature within those areas, we use our heat equation. Q, heat, equals mass, M, times change in temperature, delta T, times the specific heat of that material. But it's important to note that it's that material in that particular state. Water, for instance, has a different specific heat value whether it's in the solid, liquid, or gaseous state. The most familiar one to us is in its liquid state, 4.184 joules per gram Celsius degree. So if we look at some examples, calculate the energy needed to heat 25 grams of water from 25 degrees Celsius to 100 degrees Celsius. The specific heat capacity of water, we're reminded, is 4.184 joules per gram Celsius degree. So we know, right, hopefully, that water is in the liquid state at 25 and even up to 100. That's the typical boiling point, but it would still be a liquid at that temperature. So we are in one single phase, so we're going to use Q equals M times delta T times C sub P. Sometimes you might hear me just refer to it as the MTC equation. So substituting in the information, 25 grams for the hydrogen, 100 minus 25 degrees Celsius for the delta T, which would be 75 degrees Celsius, times the 4.184 joules per gram Celsius degree. Canceling the units out, we see that we're left with just joules. And when we consider our sig figs for our answer, we have 3 in the mass, 3 in the delta T, so therefore we would need to round the raw answer of 7,845 joules off to 7,850 joules. Example, we're told to calculate the energy needed to heat 18 grams of ice in its solid form, water in its solid form, from negative 25 degrees Celsius to 0 degrees Celsius. Again, 0 is the melting point of water, so we know that the water is consistently in the solid state. The specific heat capacity for ice, you'll notice, is different though than what we know for water. It's 2.03 joules per gram Celsius degree. So since we're in one phase, we're going to use the MTC form of the energy equation. And so substituting in our values, 18 grams for the mass. Delta T would be 0, that's the final temp, minus the initial temp, negative 25. And our specific heat, make sure you're using the right one, 2.03 joules per gram Celsius degree. Simplifying and doing the number crunching, we come up with an answer of 914 joules of energy. In this example, we're dealing with steam, 18 grams of steam going from 105 degrees Celsius to 150 degrees Celsius. Specific heat for steam is, again, different. It's 1.84 joules per gram Celsius degree. So since we are in one single phase, water boils at 100, so at 105 we know it's going to be in the gas phase, 150 likewise. So within a single phase, we use the MTC equation. 18 grams for the mass. We find the difference between 150 and 105, and that gives us the 45.0 degrees Celsius you see for delta T, and then the specific heat for steam, which is 1.84 joules per gram Celsius degree. That gives us 1,490 joules. Now we can do the same sort of thing for materials other than water. We use the same equation, we just need to make sure that we're using the proper specific heat and also make sure that the temperature range that is given is one that only involves a single phase for this type of problem. We can do them when they're going through different phase changes, and we'll look at those in future examples. But in this one, calculate the energy needed to heat 125.0 gram sample of iron from 25 degrees Celsius to 250 degrees Celsius. Now, iron, we're familiar with iron. At room temp, we know it's a solid. Most metals typically have higher melting points, and so 250 degrees Celsius is not cool, but it's also not extraordinarily hot as far as metals go. So we would predict, and we could look up what its melting point is, but we would predict that it's still going to be a solid. Specific heat capacity for iron in the solid state is 0.450 joules per gram Celsius degree. So since we're in one state, MTC is the equation we want to use. 125 grams times 225.0 degrees Celsius times 0.450 joules per gram Celsius degree. Again, the 225 was the difference between the final temp, 250 degrees Celsius, and the initial temp, 25 degrees Celsius. When we do the number crunching, cancel our units, we come up with a final energy of 12,700 joules. So when we are adding energy and we are at a phase change, again, the temperature plateaus, right? The temperature does not change. And so these are the flat areas, or the plateaus as I refer to them, where there's zero slope. And it's in these areas where we have the transition between states occurring. So there's actually two phases that are present at the same time. Now, depending on where on that line you are, you may have more of the solid state than the liquid state, or you may have more of the liquid than the solid, or you might have, an equal mix if you're right in the middle of that line. Same thing with the liquid vapor plateau, the upper plateau there. Now, to calculate the energy that's involved here, it's going to look a little bit different. It's going to look similar, but a little bit different at the same time. The energy involved is going to be dependent upon how much you have, obviously. The more you have, the more energy is going to be needed. So M, but now the second term that we have is delta H. It's an enthalpy value, so it's an energy value, and it'll be the enthalpy of fusion for melting and freezing, or the enthalpy of vaporization for condensing or vaporization. And so again, there's no delta T term because there's no temperature change. And the specific heat, again, we're going to be changing between different materials, different phases, so we're not going to have a specific heat value. So when we think about these different enthalpies, the enthalpy of fusion is the energy that's going to be required to melt a substance at its melting point per gram or per mole if you're doing a molar value. And for water, this value is 334 joules for every gram. If we want the molar enthalpy of fusion for water, it would be 6.02 kilojoules per mole. We can easily interconvert between those two values using the molar mass for the substance, water in this case, to go from grams to moles. Enthalpy of vaporization would be the analogous value for talking about the energy required to boil a substance at its boiling point. For water, the enthalpy of vaporization is 2,260 joules per gram, or 40.7 kilojoules per mole. And so if we think about some of the ramifications of this, one would be that why is it so much more energy to turn liquid water into gaseous water than it would be solid water into liquid water? And when you think about what happens in those phase changes, solid to liquid, you're merely loosening the intermolecular force attractions. They're still holding on to each other, so they haven't totally lost their grip, but there is more freedom of movement. Whereas in vaporization, what you have is the intermolecular forces are completely being overcome. And so that's going to take a lot more energy to do rather than just loosen up the connection that's there. The other thing to keep in mind is that when we talk about steam burns, okay, steam burns hurt so much because the very first thing that happens when steam would come into contact with your skin is it's going to condense. So it's going to release the energy of vaporization equivalent. And once it condenses, you still have water at 100 degrees Celsius. So now you're going to get burned by the hot water. So it's really a double whammy, so to speak, when you get a steam burn, because you have that enthalpy of vaporization energy that's going into your skin, and then you have the thermal energy of the liquid water cooling down. That's going to add insult to injury. If we reverse these processes, we would have the same quantity of energy. It's just that the sign would be reversed. So if you are going from a liquid to a solid, such as water freezing into ice, it would be negative 334 joules per gram, or 6.02 kilojoules per mole. So that would be energy given off, which may seem counterintuitive, but when you think about citrus farmers in the South, when the first freeze is coming up, they will actually go out and spray the trees. And that may seem counterintuitive because you're worried about it freezing, but as that water on the exterior freezes, it actually releases energy, and that energy goes into the fruit itself and helps prevent the internal moisture, the internal water of the fruit from freezing and thus destroying the crop.